Hello, everyone, and welcome back. I hope you're doing great. Before we begin, thank you so much for your amazing support. It really motivates me to keep creating these lessons. Now, let's start Chapter 3 Gauss's Law. This chapter is one of the most important chapters in electrostatics because it gives us a much faster way to calculate electric fields in many situations. Let's take a quick look at what we'll learn in this chapter. First, we'll introduce the concept of electric flux and learn how to calculate it. Then, we'll study Gauss's law and understand its mathematical form and physical meaning. After that, we'll apply Gauss's law to different types of symmetry, including spherical, cylindrical, and planar symmetry. These are some of the most common exam topics, so we'll solve several examples together. Next, we'll learn how electric charges behave in conductors at electrostatic equilibrium. Finally, we'll study the electric field inside and outside conductors, which is another very important concept for exams. By the end of this chapter, you'll know exactly when Gauss's law can simplify a problem and save you a lot of calculation time. So, if you're ready, let's begin with our first topic, electric flux. Now let's begin with the first topic of this chapter, electric flux. Electric flux is a measure of how much electric field passes through a surface. The more electric field lines passing through the surface, the larger the electric flux. Now let's look at the main equation. Electric flux equals the dot product of the electric field vector and the area vector. In equation form, we write phi equals E dot A, which is equal to EA cosine theta. Now, if we look at the figure, we can easily identify the parameters. The blue arrows represent the electric field vector E. The vector A is the area vector, and it is always perpendicular to the surface. The angle theta is the angle between the electric field vector and the area vector. Now let's discuss two important special cases. First, the maximum electric flux. This happens when the electric field is perpendicular to the surface. In this case, theta equals 0 degrees, so the flux becomes simply EA. Second, the zero flux case. When the electric field is parallel to the surface, the field lines do not pass through the surface. Instead, they move along it. Therefore, the electric flux is 0. These two cases are very important and appear frequently in exams, so make sure you remember them. Now that we understand the concept of electric flux, let's solve an important and frequently asked exam problem from this topic. Now let's solve our first exam type problem from this chapter. In this example, we have a square surface placed inside a uniform electric field. The side length of the square is 3.2 millimeters. The electric field is 1800 newtons per coulomb, and the angle between the electric field and the normal is 35 degrees. Our goal is to calculate the electric flux through the surface. If we look at the figure, notice that the given angle is measured with the normal, not with the surface itself. This is exactly the angle we need in the electric flux formula. Now let's solve it step by step. Step 1. First, calculate the area of the square. Area equals side squared. After converting millimeters to meters, we obtain 1.024 times 10 to the power of minus 5 square meters. Step 2. Now apply the electric flux equation. Electric flux equals the electric field multiplied by the area and multiplied by the cosine of theta. Substitute the given values into the equation. Step 3. Finally, evaluate the expression. The electric flux is approximately 1.51 times 10 to the power of minus 2 Newton meter squared per coulomb. One important exam tip before we move on. Always make sure that theta is the angle between the electric field and the normal vector. If the problem gives the angle with the surface instead, you must convert it before using the formula. Great. Now let's continue with another important exam problem. Now let's solve another important exam type problem. In this question, we need to calculate the electric flux through the top face of a cube for 3 different electric fields. The cube has a side length of 1.40 meters. Let's solve it step by step. Step 1. First, identify the area vector of the top face. The side length of the cube is 1.4 meters, so the area of the top surface is L squared, which gives us 1.96 square meters. Since the top face is perpendicular to the positive z-axis, the area vector points upward along the positive k direction. So the area vector is 1.96 k square meters. Step 2. Now, before calculating the electric flux, let's quickly review the dot product of the unit vectors. I dot I, j dot j, and k dot k are equal to 1. The dot product between different unit vectors, such as I and k, or I and j, is 0. Now we apply the electric flux equation. Phi equals E dot A. Part A. The electric field is 6I hat. Taking the dot product with the area vector gives I dot K, which is 0. Therefore, the electric flux is 0. Part B. Now the electric field is minus 2K hat. Since both vectors are along the z-axis, K dot K equals 1. The electric flux becomes minus 3.92 Newton meter squared per coulomb. The negative sign means the electric field enters the top surface instead of leaving it. Part C. Finally, the electric field is minus 3I hat plus 4K hat. The I hat component does not contribute because I dot K equals 0. Only the K hat component remains. The electric flux is 7.84 Newton meter squared per coulomb. This problem teaches us a very important idea. When using the dot product, Only the component parallel to the area vector contributes to the electric flux. Always identify the direction of the normal vector first before starting the calculation. That's it for this lesson. I hope this example helped you understand the concept more clearly. If you found this video useful, please support the channel by giving it a like, subscribing, and sharing it with your classmates. If you have any questions, suggestions, or topics you'd like me to cover next, leave them in the comments. I read your comments and they really help me improve the course. Thanks so much for watching and for supporting the channel. I'll see you in the next lesson.